or changes the gravity of the universe. So the composition, the physics of the universe is on the right-hand side of the Friedmann equation, and the kinematics is on the left-hand side. So this equation is sort of the F equals ma for the universe, where we want to learn about the composition. Now, we can't directly observe A, the scale factor, or T, time, but we can observe proxies for both of those. So instead of A, the scale factor, we observe or measure redshifts of distant galaxies. And instead of measuring the time to which we are looking, we measure distance. And through knowledge of the speed of light, we can relate that to time. And so in the observer's frame, what's known as the Hubble diagram, or redshift versus distance relation, is how we can learn about the expansion of the universe, A dot. Now, of course, if we look further into the past, by looking out in distance, we can also learn about the past expansion history of the universe as well. So we can learn about this whole function A of T. Now, it used to be that the universe was so simple.
I can put on my headphones.
Oh, somebody talking. Should I?
Sure.
I could try to mute them, or maybe Kevin can. Kevin, you might want to mute people who you see talking. Anyway, as I was saying, so therefore we can derive an equation of motion, this Friedmann equation, and we can measure the expansion rate of the universe. Now, we used to think the universe was so simple that it was matter dominated, that really all we needed to do was measure just the first two derivatives of A. The first derivative is the Hubble constant. That's the present expansion rate of the universe. It sets the size scale and the age scale for the universe. This was once debated to about a factor of 2, whether it was 50 or 100. And the second derivative, again, in a matter-dominated universe, these are the only two numbers you need to know. This second derivative is called the deceleration parameter. It is determined by the amount of matter in the universe, the mass density of the universe, which tells us how much deceleration there will be. Again, in a matter-dominated universe, knowing the total matter in the universe also tells us the geometry of space, the ultimate fate of the universe. And this also was once debated whether the universe was dense and would slow or decelerate rapidly, ending in a kind of a big crunch, or whether the universe was only lightly filled and therefore was decelerating only a little bit and would expand forever. And the 1990s was really a special time for learning about these properties of the universe, because it was the time when we got the first really long-range distance indicators, I'll refer to as standard candles, for making empirical measurements of the expansion history of the universe. So in this talk, I'm going to talk about two kinds of standard candles. So a standard candle is any object in the universe whose luminosity you understand well, or can standardize to understand it well, so that by observing its brightness, you can determine its distance. And probably our two best long-range standard candles these days are type 1a supernovae, which are exploding stars. This is a white dwarf star, the core of a star that is under degeneracy pressure and reaches the Chandrasekhar limit, probably because it lives in a binary. And so mass is transferred over. When it reaches the Chandrasekhar limit, it gives a very uniform explosion, which is billions of solar luminosities. So these can be seen very far away. The other most used standard candle is Cepheid variables. These are pulsating stars, supergiant stars that are hundreds of thousands of solar luminosities. And there's a very good relationship, very tight relationship between the period of their pulsation and their luminosity. The reason being that stars which are more massive have greater luminosities, but take longer to go through an oscillation. And the reason they have an oscillation at all is they are overshooting their equilibrium point, the hydrostatic equilibrium point, due to an opacity mechanism in their atmosphere. I could say more about that. So in practice, then, we look for type 1a supernovae or these pulsating Cepheid variables. We standardize them by measuring their periods or other properties. We use the colors we observe for them to account for, sometimes there's dust between us and these objects, but that reddens the light, so we can account for that with colors. And we're off to the races to measure distances. So fast forward to the early 2000s, and these tools were used to tell us two interesting things about the universe. One is that it was accelerating, not decelerating at all, and that was seen with high redshift type 1a supernovae. That was work that I worked on, and also that the approximate expansion rate, or the number called the Hubble constant, was around 72 to about 10% precision. We had a new model of the universe called LambdaCDM, which tried to describe why the universe would be accelerating. And so let me talk a little bit about that. So although we have this model LambdaCDM, we would still like a better understanding, and we really don't have a great understanding of why the universe is accelerating. So option one is that it is lambda in LambdaCDM. That is a cosmological constant, as Einstein would have called it, or we could just think of it as vacuum energy, a constant amount of energy in empty space, which, of course, in general relativity gives rise to repulsive gravity. That is certainly a possibility, although there's a terrible calculation or disconnect between our understanding of what that vacuum energy level should be and what we actually observe, about 120 orders of magnitude. So we're not thrilled with this explanation. The second possibility is a dynamical dark energy. So that means that there would be a scalar field perhaps in space, and the potential energy of that field could temporarily act like we had a cosmological constant, could cause the accelerating expansion. Another possibility is a modification to general relativity on large scales. And we are trying to test all these possibilities. So how do we proceed in the current era when we don't really know which of these possibilities is right? And because option one, vacuum energy or LambdaCDM, is really the easiest to calculate, we sort of assume that as the model, and then we do new experiments and look for departures from that model. So the rest of this talk, I'm going to tell you about what I think of as the ultimate end-to-end test for LambdaCDM, and that is to predict and measure the expansion rate of the universe in absolute terms. So just to give you a little more detail what I'm talking about, generically, LambdaCDM, the model, as illustrated here, starts out with the universe dominated by dark matter, neutrinos, photons, and atoms at very high redshifts in the early universe. And over time, as the matter dilutes, atoms, photons, neutrinos dilute, dark energy doesn't dilute very much. The universe becomes dominated by dark energy. And generically, this model predicts an expansion history, which is plotted here, over time that looks like this: a dark matter dominated era when the universe is decelerating in its expansion, and the dark energy dominated era we live in now where it's accelerating. But what exact expansion rate of the universe would we expect? Well, when we look at observations of the cosmic microwave background, particularly from Planck, we can use the model as it would have looked when the universe was young to predict what the scale of fluctuations would have been like in the early universe. We can compare that to the angular fluctuation spectrum we see. And in that comparison step, we can calibrate the free parameters of LambdaCDM. Once those parameters are calibrated, we collapse to essentially one specific line here, one specific expansion history. And that one, shown here, predicts that the Hubble constant today ought to be 67.4 plus or minus 0.5. And so a powerful test is to use the more direct route to actually measure, by the definition, the expansion rate of the universe. And that becomes a powerful test of this whole story about LambdaCDM and whether we have the right model and whether it's complete. So what I'm going to talk about now is a project we started about 15 years ago to try to do that, the SH0ES project, whose goal was to reach percent level precision in local measurements of the Hubble constant. And the way we proposed to do that was to use what's called a distance ladder, which I'll describe, sort of gold standard tools for measuring distances. So that's using basic geometry to calibrate the luminosity of Cepheid variables, which I described, and use those to calibrate type 1a supernovae, which can be seen out much further to measure the expansion rate of the universe. We saw ways to reduce systematic errors by collecting the data in a consistent way. I'll describe that, as well as by making observations in the near infrared to reduce or mitigate the effects of dust. Also through strict propagation of errors, and particularly keeping track of covariance so that we can get a realistic uncertainty. This is a Generation 2 project using the Hubble Space Telescope. Generation 1 was the original efforts to measure the Hubble constant to 10% precision. This was a series of competed proposals, about 20 proposals now, and it has now taken up about 1,000 orbits. So it's a lot of time on the Hubble Space Telescope. Okay, so let me tell you a little bit about distance ladders. Distance ladders are simple and empirical, but the key element is they need to be measured or applied in a consistent manner. So let me describe our distance ladder, which is basically 3 steps. The first rung is where we use geometry, and this can be done many different ways to reach the distance to Cepheid variables and calibrate their luminosity. That I refer to as the anchor step, and is done at distances of kiloparsecs to megaparsecs. Step 2 is to identify galaxies nearby which hosted a type 1a supernova, where we can go back with the Hubble Space Telescope and find Cepheid variables in those galaxies and calibrate the type 1a supernovae. And then finally, type 1a supernovae can be seen at high redshift. We don't go to too high redshift because we want to measure the present expansion rate, not the past expansion rate. And so we do that out to about a redshift of 0.1. So there's no astrophysical modeling involved. This is purely empirical. There's virtually no general relativity or LambdaCDM involved. I say virtually none because if we could do this at redshift 0, there would be none. We do it at very modest redshifts. However, it's critical to measure the objects across rungs in a consistent manner, and I'm going to talk about that, but we spend a lot of effort in this project to do just that. So let me start out with rung 1. What do I mean by we use geometry to measure the distance of Cepheid variables? Well, the most basic way to use geometry is to measure trigonometric parallax. And so we can look at distant stars like Cepheid variables and measure their trigonometric parallax, the angle through which those stars move over the course of a year as the Earth goes around the sun. And the inverse of parallax then tells us the distance. The problem is that most long period Cepheid variables in the Milky Way are very far away. They're kiloparsecs away. And so the parallax angle is very, very small. It's a fraction of a milliarc second. Or for a 1 sigma measurement would be about 1/100th of a pixel movement of that star on the Hubble Space Telescope. So we need to measure positions to very high precision. So we developed a new technique for doing this about 10 years ago with the Hubble Space Telescope, and that was to spatially scan or drift scan the telescope during the observation so that the stars move by and you can measure the changing separation of the stars over the course of a year to much higher precision than you can with just staring mode observations where you have less pixels involved in the measurements. With this technique, we found we could get to 20 to 40 micro arc seconds. So that's quite good. That really does get us in the neighborhood of the precision we need. So what I would call approach 1 is to use the Hubble Space Telescope spatial scanning. And what I'm showing here are about 8 Milky Way Cepheids, long period Cepheids. There's a data point every 6 months, and this back and forth motion you see is the parallax. The amplitude tells us the distance. And we did that to about 3% precision in the Hubble constant a few years ago. This has been overtaken by what I would call approach 2. Approach 2 is to use a new European satellite named Gaia that is measuring very precise parallaxes over the entire sky. And we picked 75 of those and observed their fluxes with the Hubble Space Telescope so that, again, we can compare them to distant Cepheids on the same photometric system. So this is part of reducing systematic errors, is using the same telescope to make the measurements of the same kind of object across rungs of the distance ladder. And that has worked quite well. And then most recently, just in the last few months, what I would call approach 2.5, it still uses Gaia parallaxes, but there are a couple dozen Cepheid variables that live in star clusters, what are called open clusters. And these clusters have hundreds or thousands of bright stars. And instead of being limited to the parallax precision of a single star, the Cepheid variable, we can average the parallaxes of hundreds or thousands of stars in these clusters to get down to about 10 micro arc seconds in the parallax of a couple dozen Cepheid variables. So these techniques now using Gaia have gotten us to 1% precision. And so what's called the period luminosity relationship of Cepheid variables that I alluded to earlier in my talk, the way we standardize them, can now be done directly with parallaxes in the Milky Way, both calibrating them and measuring this relationship. And so, 10 or 15 years ago, this was unheard of to be able to measure the parallaxes of Cepheid variables. And now it's done very well. And so you see these 3 generations of measurements I talked about. In purple, the ones we did brute force with the Hubble Space Telescope. In green, the ones Gaia has measured for 75 Cepheids. And in red, the ones that live in clusters where we get even smaller scatter because we have better parallaxes by averaging over the whole cluster. And when Gaia reaches its final expected precision in another 5 years or so, this should be good to about 0.4% in the Hubble constant. Okay, so this is just one way to geometrically calibrate Cepheid variables, measure parallaxes. Another technique that's very powerful is to measure a geometric distance to a nearby host, like the Large Magellanic Cloud, that has many Cepheid variables in it. And people can measure the geometric distance to the Large Magellanic Cloud by measuring systems in that cloud called detached eclipsing binaries. These are stars orbiting other stars. And by measuring the timing of the orbit that's done through the eclipse event, one can use Kepler's law and geometrically measure the distance to the Large Magellanic Cloud. And a third method that's very powerful is to measure water masers in Keplerian motion around a supermassive black hole in another galaxy, NGC 4258, and use that to calibrate the Cepheids in that galaxy. Somebody named Tara Drake, if you could mute, that would be fantastic. So we can use these 3 different techniques to get calibration that's good to 1%, 1.3%, or 1.5%, depending on which of these techniques we use. Okay, so step 2, as I said, is to look at galaxies at intermediate distances that hosted type 1a supernovae and go back and observe Cepheid variables in those galaxies. Now we're limited in range to about 40 or 50 megaparsecs. That's how far out we can see Cepheid variables with the Hubble Space Telescope. And there's a good type 1a supernova in that range about once a year. So we've now calibrated all, I would say, 42 type 1a supernovae that have gone off in the last 40 years in that range that are suitable. And that number has grown quite substantially by going back and calibrating those in the last few years, so that by now in 2022, we're up to 42 type 1a supernovae that have been calibrated with Cepheid variables, and this contributes about 0.9% uncertainty in the Hubble constant. And I want to mention Wenlong Wan, who was a postdoc working with me, who's helped develop the pipeline that we use to find the Cepheid variables. Let me say a little bit about Cepheid variables. So these are the host galaxies. We come back with the Hubble Space Telescope and we find the Cepheid variables. Where you see the red dots there are the locations of Cepheid variables in these galaxies that previously hosted the type 1a supernovae. We find Cepheid variables from their variable light curves. So what I'm showing you here are the composite light curves of all the Cepheid variables in an individual galaxy. They have a very characteristic shape, this kind of sawtooth shape where they rise fast and decline slowly. And then we measure the period luminosity relationships, like I showed you for the Milky Way, in all of these distant galaxies, so that we can directly compare those and measure the distances. Now, as I described before, but I wanted to emphasize here, One of the great improvements here is we measure with the Hubble Space Telescope the Cepheid variables using the same instrument and filters in the anchor galaxies and in the supernova hosts, so that again, these are directly comparable. And we make our measurements in the near infrared to reduce the effects of dust. And so what I'm showing you here are the period luminosity relationships for Cepheid variables in the Large Magellanic Cloud. And as you go further and further to the red, as you go from optical wavelengths here in orange all the way to the near infrared here, or D-red and near infrared, you can see the narrowing or the tightening of the period luminosity relation, because we're getting rid of the effects of dust and we're getting right down to the physics of the Cepheid variables. Okay, step 3 is to measure the expansion rate of the universe now using type 1a supernovae. This has been done many times, of course, but there are now expanded samples like the Pantheon Plus sample that we use to make this measurement. We're essentially figuring out what is the characteristic brightness of type 1a supernovae at a given redshift. Generally, one cannot do this exactly at redshift 0, so there are higher order corrections I'm showing here for the deceleration of the universe, or even the third derivative of the expansion rate, what's called jerk. But these have a very small impact. That's why I said that it's sort of at the 1% level, the contribution of things beyond the Hubble constant to this measurement. We don't want to measure too locally because we'd be sensitive to local motions or flows in the universe. And as I said, we don't want to go to too high a redshift, so we're not sensitive to these higher order corrections. So a few hundred type 1a supernovae at sort of intermediate redshift are what we use. So then putting all of this together in one step, this is what we call the 3-rung distance ladder from the SH0ES team, using geometry many different ways to calibrate Cepheids. That's rung 1. Rung 2 is Cepheids versus type 1a supernovae to calibrate those, and then type 1a supernovae versus redshift to measure the expansion rate. And so this is one distance ladder then that reaches out to the expansion Hubble flow of the universe. But we have gotten much more sophisticated in our analysis in the last few years. We've now fully characterized the covariance of data, both of Cepheids and type 1a supernovae. So I'm showing you the covariance matrix of our distance ladder. This is based on 3,200 Cepheid variables, some 300 type 1a supernovae, and there are 5 free parameters in the fit. 2 are just the fiducial luminosities of our standard candles, type 1a supernovae and Cepheid variables. 2 are parameters that characterize Cepheid variables, the slope of their period luminosity relation, and any dependence on chemical abundance or metallicity. And then we run an MCMC so we can properly measure the, I'm sorry, I forgot to mention the 5th parameter. That one is 5 log H naught. And so that, of course, is what tells us the Hubble constant. So we can also measure the covariance between the model parameters. That's can be important in some cases as well. Okay, so jumping to the punchline, the answer we get is 73.04 plus or minus 1.04, including systematic uncertainties. By running 100 million chains, we can sample the tails and see to a pretty good precision now that we are really 5 sigma from the predicted value of the Hubble constant that I mentioned earlier, using Planck and LambdaCDM. We get a very good fit to our data, so we don't have no excess variance, and the uncertainty has now come down from, in 2016, just we were at 1.7 uncertainty. Okay, so just going over some tests of robustness of this result, we can separate the result based on different ways of geometrically calibrating the distance ladder. So the 3 primary ways we use up here, looked at individually, give values for the Hubble constant like I show here. They're all quite consistent. And then we have also some independent checks from other techniques that we don't use as primary anchors, but we can use them as cross checks. They're less precise individually, but it doesn't look like the result is coming from the effect of any one of these anchors. So that's very important. They're all quite consistent. We also do various validation tests of our photometry, our ability to measure the brightnesses of the Cepheid variables. And so I'm showing you just a couple of those tests, but there are many more in the paper. For example, do we get consistent measurements of Cepheid variables in high density backgrounds versus low density backgrounds where the measurements are easier to make. And so we can compare those within the same galaxy. So I'm showing an example here, and they're very consistent to about 100th of a magnitude. We have many other tests. Another one is a null test where we look at the residuals from the global fit to the distance ladder versus the local background measurements. Now, if we were overestimating the background in the supernova galaxies, then we would expect the data points to follow the red line. If we were overestimating in the anchor galaxy, NGC 4258, we'd expect the black points to follow the black line. And instead, we see everything's quite consistent with 0. It's also hard to cook up a way where you would overestimate the backgrounds in galaxies that hosted supernovae, but then not do the same in the maser host NGC 4258. So this is a pretty strong test at this point. And at this point, we can really rule out impact of this as a systematic. Okay, so in the paper, we go through 67 variants of the fundamental analysis that we do, including bifurcations of the data and extensions. And I don't have time to go into all of those, but I'll just show you some of the ones that people have been most interested in, different ways of either removing outliers, different geometric anchors to use, ways of relating color to dust, within some reasonableness, the use of metallicity to refine the standardization of Cepheid variables, which sets of supernovae we use. And the bottom line here is it's very difficult for us to get below about 72.5 or to really get much above 73.5. The additional scatter from the systematic variance we propagate as additional error in our measurements. Okay, so at this point, I could go through lots of questions that people might have or try to anticipate them. I'll just mention a few and maybe come back to these if people have these as questions later. Could we live in a giant void? And so the universe is rushing out around us, about 9% in the Hubble constant. The answer here is no, both from large-scale structure theory and both from direct measurements from the Type 1a supernova Hubble diagram. There could be maybe 0.6% uncertainty in the Hubble constant, but it would be about a 15 or 20 sigma strangeness to live in such a void in the large-scale structure we see around us. Is the Hubble Space Telescope linear enough to make a measurement this well? Yes, actually, it's been calibrated to about 0.3% in our ability to measure the Hubble constant. This is something I do as part of my functional work at Space Telescope Science Institute. I mentioned about the backgrounds of Cepheids, so I think I've addressed that one already. Are there differences in the supernovae across the distance ladder? We put a lot of effort into this, and if you read this paper by Jones et al., you can see there are no correlations in the Hubble residuals to maybe 0.3% in the Hubble constant. Are the different anchors consistent? Yes, really to better probably than one sigma at this point. Are other ways of measuring intermediate distances like tip of the red giant branch and Cepheids consistent? Yes, they are. If you start from the same anchor and go to the same host, you get very consistent results. And this is covered in a couple of papers, or I could say more about that. Can you resolve the tension by changing dust laws in each of the hosts? No, because we're already observing in the near infrared. So the effects of dust on the Hubble constant are already at the 1 or 2% level. And so errors we make in that are smaller than that. And this is a 9% problem in the Hubble constant, but there's also a number of different papers about that as well. Okay, I wanted to say something about JWST. What will JWST do for this problem? This, of course, is a new telescope which has been launched and has greater resolution. I mentioned before about dense backgrounds with Cepheid variables. One of the nice things about a higher resolution telescope is it de-densifies, or it makes it easier to see individual objects like Cepheid variables in dense regions. And so we can do a test of what ought to happen when we use JWST simply by taking the data that we have and progressively eliminating the most crowded objects. And when we get down to about the least crowded or most empty, like you see on the left here, third of the data, that's the kind of resolution that JWST will give us. Now, when we do that, we see no pull on the Hubble constant. The value we get is very similar to that. However, even better, oh, sorry, one more test we did is to use the most crowded half and least crowded half of the data. That has very little effect. But even better than trying to anticipate what the James Webb Space Telescope will give us would be to actually use the James Webb Space Telescope. So we got lucky a few weeks ago. Somebody took a serendipitous observation. So I should say, we have a large program in the first year with JWST to reobserve these galaxies and remeasure the Cepheid variables. But that's going to take a while just to get on the schedule and have those observations occur. However, there was a serendipitous observation of one of the galaxies. We observed a type 1a supernova host that had Cepheid variables that we previously observed with the Hubble Space Telescope. And even the serendipitous observation was enough to observe a good handful of Cepheid variables. So this purple rectangle you see is the JWST near-cam footprint. And what we observe with HST is this square you see over here. And you see a little bit of overlap here of Cepheid variables. So if I zoom in on some of those, you could see how exquisite the resolution is of JWST. Here are known Cepheid variables. They're known from their position in the optical. And when we follow them up in the near infrared with the Hubble Space Telescope, you could see the lower resolution and the undersampled pixels gives you effectively poor resolution of those. But with the James Webb Space Telescope, we have much higher resolution and we could isolate them better. And we did this with just this first galaxy, and just showing you the period luminosity relationship we have from Hubble in gray versus JWST in red are very consistent. In fact, we just submitted this paper and put it on the archive last week. The intercept we get is very similar. We see no evidence of it would require a shift of the red curve here to the dotted line, to the middle of the dotted line, in order to suddenly find that the Cepheid variables seen through JWST were quite a bit fainter than they were seen through Hubble. That would explain the Hubble tension. So that certainly in the first observation doesn't look likely. Of course, I've been talking a lot about the work we've done with this technique or these objects. Of course, many other groups have either used our data and reanalyzed it or collected their own data in different ways. And this Hubble tension, this difference between what is predicted and what is observed, is not just seen by us, but seen by pretty much everybody who uses this data. This is sort of the last 20 years of observations. The difference here just is over time, the measurements have been getting more and more precise, but the central value hasn't shifted very much. There was even a team recently that went back to the Hubble archive and took the individual pixels and reproduced the measurements that we got in this paper from the Arakaria project. And so this really does look like what the universe looks like on the sky, I would say. And again, it's not just even this technique, but many other techniques. If you make that prediction from the early universe using Planck or WMAP or ACT, any of the CMB experiments, or Big Bang nucleosynthesis, anything from the early universe to calibrate the model and predict the Hubble constant, you're going to predict something around 67 to 68. Whereas the measurements locally, the direct measure, depending on what techniques you use, vary from about 70 to 75, with the 73 that I've talked about being not only the value we get, but a pretty fair average of the different values. So this problem has become called the Hubble constant tension or discrepancy or crisis, whatever you want to, whatever term you like. It doesn't seem to depend on any one method, any one team, any one source. You can eliminate any certain kind of data and you're still left somewhere between 4 to 6 sigma in significance. So the community is very intrigued by this because it smells like, or it could be, new physics in the universe. It could be a missing component of LambdaCDM or some wrinkle in LambdaCDM that is confounding our ability to start at the early universe and predict the expansion rate today. Right, these are the two measurements I've been focusing on, but I talked about the others. There's also a second tension that looks similar. It's a little less significant, but it's similar in many ways. And that is when you compare how clumpy the universe is on 8 megaparsec scales, a parameter known as sigma 8 or S8, you can likewise predict how clumpy the universe ought to be through expansion and dilution and gravity or you can observe it through other techniques, weak lensing and clustering. And again, just like I showed you with the Hubble tension, systematically, locally, you see a different value for this S8 parameter versus what you expect it to be from the early universe. And this is seen, I would say, at 3 sigma by multiple methods. So all in all, it's probably 4 sigma at this point. So it smells like the Hubble tension. And so people have tried to think about solutions that could explain one or both of these, and it's hard. There are lots of ideas. Francis, who is at New Mexico, now was at this conference a few years ago and has some ideas that I think are quite interesting. Some of the ideas are weird neutrinos, decaying dark matter, another episode of dark energy early in the history of the universe. Some ideas work better. They don't conflict with other measurements. Some are worse. I list various ones. There are many reviews in the literature. I can't do justice to this topic, but I'll just mention a review. I'll also mention that the most likely solutions are the class of solutions which alter the universe when it was young, before recombination, that in particular cause the universe to expand faster at early times, to make it become transparent earlier, that shrinks what's called the sound horizon, the distance that a fluctuation can travel between the Big Bang and when it becomes transparent, essentially changing the calibration of the cosmic microwave background and the expected value of the Hubble constant. There's been some claims in the literature of even seeing independent evidence for this episode in parts of the power spectrum of the CMB. I think the jury is out on that, but people are paying close attention. So what do we do now? Well, at this point, I think we need some very specific hypotheses because the data has gotten very good, and this is a very challenging problem. So it's easy to say, well, it looks like new physics, but because the data is so good, we need a real detailed explanation of what that is to see whether it would actually pass the data. It's easy to say, well, it just still sounds like systematic errors in measurements. The problem is there's so many independent measurements, independent rungs and duplicate measurements, that short of a catastrophic failure of the Copernican principle, I haven't heard of a hypothesis that of a systematic or systematics that could actually explain this without a lot of conspiracies. So at this point, it's clear there's some kind of signal, and it really requires a specific and testable explanation, and also likely more data. So we have continued to chew away at our error budget. I'm showing you the evolution of that. All our terms are now below 1%. There are a few things on the horizon, like Gaia, data release 4 and 5. LIGO can contribute to this. New missions, DESI, LSST, Roman, Rubin, and Euclid. These are all ways of better characterizing the expansion history recently. Next generation cosmic microwave background experiments could see signatures of, for example, early dark energy or some kind of weird neutrinos. So this is an interesting problem worth staying tuned to. So my final thoughts, and then I'll just take some questions, is this discrepancy. This discrepancy is about 5 sigma at this point. Another way to describe this is there's really no precise measurement of the Hubble constant coming from the late universe that comes in any lower than those from the early universe. That's just another way of saying, you know, everything's pretty much on one side or the other side, split by whether it's early or late. It appears robust, this tension, because it would require multiple catastrophic failures to avoid it. And I think it's really interesting, unless, you know, you're you just love and believe deeply in LambdaCDM at more than 5 sigma, or you're willing to discard a lot of data. This is an interesting problem. And I think it's always important to remember LambdaCDM itself is not Maxwell's equations. It's a fitting function. It has a lot of phenomenology, but it's missing a lot of basic physics. 95% of it is dark. We don't have quantum gravity. And so it's not crazy to think that there's something missing with LambdaCDM and that these tensions could be clues to those. So I will end there and happy to take any questions that you have.
Yes, well, let's have questions. I should probably try to unmute everybody, but I don't know quite where to click to unmute everybody. So why don't you just unmute yourselves, try to do that if you want to ask a question, or you can use the chat. And of course, let's thank the speaker, Adam Riess, for a marvelous colloquium. And let's have some questions.
Don't be shy. Anybody jump in?
I have a question.
Yeah.
Can you hear me?
Yep.
Yeah, so right at the very beginning of your talk, you showed the 67.4 that we were looking for. That was an assumption of the presence of LambdaCDM. I was trying to understand if you take away is there such a meaning to taking away the effect of lambda? What would you have predicted without lambda? Not 67, but some other number. I just didn't know that right at the very beginning.
Yeah, that's an interesting question. I mean, basically what you're doing is, the expansion rate is decreasing, and then at some point it actually starts to increase again because of lambda. If you didn't have lambda, you just had dark matter, it would decrease much more, and you probably would have a much lower Hubble constant.
Okay, thanks.
Kevin, I have a question.
Green, do you want to raise a question?
Yeah, can you guys hear me all right?
I can.
Okay, cool. Well, great talk, Adam. Thank you very much. So I've now had the pleasure of attending a talk by you now, and also by Wendy Friedman. And I have a concern with, if you could go back to that De Valentino plot.
Sure.
So
hold on.
Yeah,
Sorry,
no worries.
Yep. Almost there. There.
Perfect. Okay, so if we compare the indirect, late universe or early universe measurements with the late universe measurements, we see that the tip of the red giant branch and the Cepheids are statistically similar, and that the red giant branch is also statistically similar with early universe measurements. But the transitive property doesn't work here, obviously, because the early universe isn't consistent with Cepheid measurements.
Right. If you didn't have, there. Okay, go ahead. Sure.
Yeah. So what do you think is causing the slight systematic suppression of H0 from the tip of the red giant branch method?
Yeah.
Because I asked Wendy the inverse of this question, so I'm interested in your response.
Sure. I have a backup slide. Let me see if I can find this quickly. Hold on. So right. So here. Okay. So when we measure Cepheid distances versus tip of the red giant branch to the exact same galaxies, starting from the same anchor, going to the same supernova host. So this is basically only the second rung, the middle rung.
Yep.
Right. And there are only about eight or nine galaxies that have both measurements.
Yep.
You get very consistent results, and that's what I'm showing right here. Okay. But
yeah, so it's interesting because
but there are other factors which go into the calculation of the Hubble constant. So this is sort of a I don't know, I would say misnomer or something when somebody says, what does tip of the red giant branch give, or what do Cepheid variables give? They are only the second rung. They're only the connective tissue there. There's still the geometric part. How do you calibrate it? And there's the type 1a supernova part. What do you use beyond there? And there are some differences. And so I'm going to show you some of those differences. This is in our paper. But there's two different groups that have measured tip of the red giant branch Hubble constant values. Okay. There's what you mentioned was Wendy Friedman's group that gets about 70. But there's also the EDD group that uses tip of the red giant branch. And these are two different techniques for fitting tip of the red giant branch. These folks use edge detection, and these folks use maximum likelihood or luminosity function fitting. And already that difference there is about 70 to 71.5. Okay. And if we use the same anchor, the same first rung as these folks, we get 72. Okay. So these are at this point not very different, not even, a sigma difference. Yeah. However, let me go one step further. And another piece of this puzzle is there are differences in the calibration, the first rung for tip of the red giant branch, not Cepheids, but tip of the red giant branch. So tip of the red giant branch, if you're not familiar, but it sounds like you probably are, it's not a star. There's no tip of the red giant branch star. It's a feature in the distribution of a large number of stars where you see a break or a change. And so because of that, you can't measure the parallax to tip of the red giant branch like you can for Cepheid variables. So it's harder to calibrate tip of the red giant branch. You need to know the distance to, let's say, another galaxy, absolutely, geometrically, or to a group like a globular cluster or something. And so what I'm showing you here are the last few years of efforts of calibrating tip of the red giant branch. And you can see that there's a range here, and the range is reflected then pretty well in the Hubble constant that you can get. So at the most luminous end, which is what for example, Wendy Friedman's group are all these points at the highest end, are this red dash line that gives you about H0 of 70. But there are other groups that have gotten things that are a little bit fainter, 73. Even if you're in the middle here, which seems most likely, you're in between those. So between the calibration issue and some whether you're actually comparing not just tip of the red giant branch and Cepheids, but the same first rung and third rung, the differences are very minor.
I see. That's a great explanation. Thank you. I have a second question
Sure, go ahead.
if that's all right.
Yeah, absolutely.
So this is switching gears a little bit, but George Estafio and other cosmologists have emphasized this need to include higher redshift supernova in the Hubble flow data that you use in that third rung on the distance ladder.
Yes, that isn't exactly what they've said, but what he has said, and it's a very good point, is if some astronomer, if we measure the expansion rate of the universe, let's say by measuring, calibrating type 1a supernovae at low redshift, let's say redshift 0.05, 0.1, and then somebody else wants to measure the equation of state of dark energy by comparing the low redshift supernovae to the high redshift supernovae, then you can't just use the Hubble constant and that measure of the equation of state of dark energy as though they're independent things, because they're both utilizing the same low redshift sample. And so we think we've addressed this. This is just more of a bookkeeping problem. Let me see if I have I may have a backup slide on this. I should. It's a nice figure in the paper. No, that's not it. Hold on. Kind of not there. Okay, I'm not finding it yet. Anyway, the basic idea is that you have to do good bookkeeping to compare these things. And so what we offer now is just the absolute distances to the host galaxies and a set of consistent type 1a supernovae, so that you can fit your arbitrary cosmological model simultaneously to marginalizing over the Hubble constant, and do those properly with their covariance. And so, as I said, it's really a bookkeeping problem. And I think what George was pointing out was people were ignoring the bookkeeping problem.
I see. Awesome. Well, thank you once again. This is a great talk.
So let's see, perhaps there's another question from someone else.
Coming back to the James Webb. So basically, you've done some preliminary studies that show that with the additional resolution, you're not necessarily expecting any kind of different results. No surprises there, you're saying? Are you crossing your fingers that somehow you'll be proved wrong, or do you expect nothing new to come of the James Webb in this?
I mean, I think we will learn things, and I think we will learn things that are relevant for this problem. What I suspect is that we will learn things that will allow us to get down to 1% in the Hubble constant. I don't think we're going, from what we've seen already, I don't think we're going to see a gross order shift that explains the Hubble tension.
Right.
So I think it will be helpful as we try to get down to, do even better, but I don't think it's going to be a big reset of this. I mean, at least from the first data we've seen, it doesn't look like it. And from the tests we've done, we wouldn't expect it, but that's still why you do the measurements.
Thanks.
maybe I'll ask a question.
Sure.
Could you explain a little more what S8 is and
Yeah.
how it might how you might explain both it and the Hubble trouble?
Right. So S8 is you could think of it as the standard deviation or variance of the density of matter on 8 megaparsec scale. So if you can imagine, patches or cubes 8 megaparsecs across, it's the statistical variation in the matter density in those different cubes. And so in a clumpy universe, sigma 8 will be very high, and in a smooth universe, it will be low. And so what we see between the Hubble tension and sigma 8 is we live in a faster expanding and smoother universe than we expected. And it's hard to cook up theories that do both of those things. Not saying that there aren't any, there are some, but it hasn't been easy for people to come up with ways that doesn't, at the same time violate other parts of the cosmic microwave background data, for instance.
But when you say 8 megaparsecs, do you mean 8 megaparsecs now or 8 megaparsecs?
Right, it's 8 megaparsecs now, but it's arbitrary. It's kind of the arbitrary place that power spectra are often normalized, so it's given as the reference point.
But 8 megaparsecs now would have been, I don't know, a few meters back, or not a few meters, but kilometers. I'm not an astronomer, but it would have been a much shorter distance back at the time of 380,000 years.
Sure, but we know that, so so that's in the calculation as well.
So what do you mean? Do you mean the corresponding? Do you mean?
Yeah, what we mean is we can make a prediction. We can see how clumpy the universe was on real scales back then, and then our understanding of gravity and dilution allows us to predict on 8 megaparsec scales. This is linear theory, and so there's no complex interactions to deal with. We can figure out how gravity evolves the large scale structure of the universe, so that how it would look on 8 megaparsec scales.
So both S8s are on a scale of 8 current megaparsecs.
Sure, yes, that's right.
Okay.
Just like Hubble constant predictions from the cosmic microwave background are at the present time.
Sure. Yeah.
Not in the past.
Okay. So both are predictions of what we see now.
Yes.
Okay, thank you. Let's see, there must be.
I have another question,
Sure.
but I don't want to dominate the time.
No, go ahead.
Okay. So almost an opinion question. So going forward, what do you think is the most promising direct geometric measurement technique of the Hubble constant moving forward? Do you think that the most promising technique is going to be with gravitational waves or with like the
Right. So there's two
holy
things
cow.
that I'm aware of that are intriguing. One is, can you see this data point that says masers here in
Yep,
orange?
sure can.
Okay, so that is using masers out in the Hubble flow, and this is purely geometric. It's not a distance ladder. It's a one-step geometric method out into the Hubble flow. It's been measured by the Maser Cosmology project using, I guess, VLA or VLBI measurements. And my understanding from the people who make those measurements in the radio is if they substitute the EHT, the Event Horizon Telescope, this sort of all-Earth telescope that's been used to resolve down in the core, black holes in the Milky Way and nearby galaxies. If they use that instead of the VLBI for the maser measurements, for the same set of masers, they'll get much higher resolution. They'll get down to a few percent per maser. And even with these 6 masers or so, this should give you, a factor of a few improvement in this measurement, the one you see in orange, which that should be pretty definitive then at that point. So that's one technique I like. And another one is the use of LIGO to measure standard sirens, gravitational wave from in spiraling neutron stars, kilonovae, with optical counterparts. That's been done once for an event in 2017, and there was an expectation that there'd be a lot of them by now, but there just haven't been, and LIGO's been offline. But I'm optimistic in the next 5 to 10 years, that method can be fairly definitive as well.
Okay. Cool. Thank you.
So we have time for some more questions. Does somebody want to speak up? I would think one of our astronomers would want to say something.
Well, we're at the end of the hour, so that's okay. And people can feel free to email me any questions that you have if you felt too shy to speak. Thank you very much for having me.
Well, thank you for an excellent talk. Excellent physics and astronomy, and it was very kind of you to do this. And so let's all thank Professor Riess, either virtually or acoustically. So thanks very much, and I guess I'll stop the recording.
All right.
And unfortunately, I started the recording about 2 minutes late, but the meat of the talk got recorded. As I said, I only missed 2 minutes, and one of those was probably me, so that doesn't matter.
Very good. All right, everybody, take care.
Yes. Goodbye.
Bye.